Hi everyone, so today we're going to learn about u-substitution, which maybe some of you have already done depending on how far you got in your Calc 1 class. But if this might be a review for you, fine, but for those of you who is new to you, this is going to be our first new technique of integration. It's also going to be used a lot. It ends up being that we learn a lot of different techniques of integration in this class. This particular one is one of the most simple ones, and whenever you can use a simple technique, it's great, right? So the idea, I want to motivate it first with an example, and then we'll talk a little bit about where it really comes from. But the idea is that if I have some kind of more complicated integrand like this one here, it doesn't really fit on our little table of integrals that we had. It's too complicated. But if we think back to the chain rule and how derivatives work and the fact that we're actually kind of undoing the derivative, you can see that this particular one has some sort of pattern. It really is like a chain rule thing happened here because you've got this stuff inside the parentheses and then this stuff outside is kind of like the derivative of the stuff inside the parentheses. All right, let me actually make it a plus so it really is the derivative. Of course, we can always throw in a negative and we'll do that. But just for this very first example, let's make it easy. All right, so here's my thing. And so I basically want to undo the chain rule and get that action out here. So how am I going to do it? We call it u-substitution. We're going to substitute another variable. That stuff in the parentheses, I'm just going to call it u. Now, if I take the derivative, and I'm going to use the Leibniz notation, and you'll see why. If I take the derivative, I get 3x squared, right? Well, here's my 3x squared, and here's my dx. So I can move this dx over to the other side as a differential, right? And if I really want to be very clear, I can rewrite my integral. And collect this 3x squared with this dx. Right? So now, all of that garbage at the end just becomes the du. And if I look at this just looks like u to the 5th du. Because I'm substituting in u for this, and my du becomes this whole bit here. See? Now, at first you may find it helpful to rewrite it from here to here so that the du is together, but you don't have to. You can go directly from here to here. I would like you to write down your substitution for a while, okay? You will get to the point where you can kind of do this in your head, but for now, it's really good to write down the substitution and then directly substitute it in. So, but now we're in a situation where we know how to do this integral because this is one of the ones on our sheet, right? It's just x to the n, right? So what we end up with, I integrate this, I get 1/6 u to the 6th plus a constant, okay? But of course, I don't want to leave my answer there because I started out with x's, so I need my final answer to be in terms of the variable x. So I'm going to just shove back in what x was. 4 plus x cubed to the 6th plus c. So that is my final answer. Okay? It's pretty straightforward. The difficulty with these, as you'll see as we go through more examples, is going to be what's the right substitution. The first thing to usually try is if there's some expression in the parentheses, that's a good thing to try. Sometimes there isn't. We'll see some examples shortly. But before I do some more examples, I just want to go into what we're really doing here, because I already said it, right? I said we're undoing the chain rule, okay? So what do I mean by that? I mean like this. If you remember, if you have some sort of composite function, I take the derivative with respect to x. What do? I have the derivative of the outside function times the derivative of the inside function, right? So, but that's exactly what we're doing, because what we saw there was something of this form. And what I'm really doing is I'm going to be making the substitution. U is that stuff in the parentheses. Then du dx is g prime of x, which gives me du is g prime of x dx, right? So this is exactly what we did, but now this is this is in the general form. If I stuff this in, I have f primed of u du, fine. If I know how to integrate, well, I know how to integrate because I see that it's f prime, then I get f of u, but that really is f of g of x. So I've basically undone the chain rule. And this is going to work as long as your f is continuous and your g is differentiable, and pretty much that's where we're going to be. So you shouldn't really have to worry about the details so much as you can worry about just sort of the method of making this u substitution. All right, let's do more examples. There are more. Here's another one. Now put minus in there. Okay. So again, the first thing I probably want to do is I see cosine of something, so that tells me, oh, well, let me just put whatever's in that something in the parentheses. I'm going to try, see if that makes my life easy if I make that u, right? Then du dx is going to be minus 4x, right? So du is minus 4x dx, fine. Of course, I don't have a minus 4x dx. What I really have is an x dx, right? So I need to substitute in for x dx, so this is just some number, so I can throw it on the other side, right? So I will almost always, you'll have to manipulate a little bit at least with the du, because there's often constants mucking up the works. Now I've got a 1/4 du is equal to x dx. And I did that precisely because I know, let me rewrite it so you can see it. If I put that x here, x dx, this is what I want to substitute for. Constants, I can throw them around as long as I take care of them. The x and the dx, you have to be pretty careful with that. You can't just like multiply by another x or something, right? But, you know, I can pull the 1/4 over here. So when I make this substitution now, when I put everything into u, I have cosine u, and then I have, right, so cosine u, and then here, I'm going to have minus 1/4 du. And my rule doesn't care about the constant, I just throw it out front. Okay? And again, the time will come where you can go from here, write this down, go directly there, you don't have to write down all these intervening steps. But we will do that today. Okay, so integrate. So the derivative of sine is cosine, right? So this is going to be sine u. And then I put back in what u is, like so. And there's my final answer. Okay. All right, I'm going to do one more example, and then I'll do some more examples in the second video, so these don't get too long. So, earlier I said sometimes you'll just be able to immediately see what u is. Other times you might have to do a little work to figure out what the heck to do. One example of a pretty common integral, so you should know how to do it because it pops up all the time, tangent of x, okay? But tangent of x, it's not secant squared, right? The derivative of tangent is secant squared, not the antiderivative. This, if you look at your table of integrals, is not on there. Okay? So what do you have to do? Well, oftentimes with these, with the trigonometric functions, we have to use some sort of identity. So let's write what tangent is. It's sine over cosine. And now, this is sort of thing, you will see a lot of, you'll see these fairly often. It's not explicitly like that first one where it was something to the fifth, but really when you have something in the bottom, it really is like to the power of -1. So you can think of something with the bottom, a very good choice for trying to see if this works, if this u-substitution works, is to make u equal whatever's in the bottom of the fraction. In this case, cosine x. Then if I do du dx, the derivative of cosine is negative sine. So I have sine x dx, right? So that would give me minus du equals sine x dx. Really, because this sine x is in the top. So if it makes it easier for you to see that, you can write it like this, right? Or sometimes people just put the dx in the top. Really, whatever. You don't have to write it like that if you can just see it here. Once I make my substitutions, you can immediately see it as minus du over u, right? Because sine x dx is minus du and the cosine is u. So this is minus natural log of u. So your answer is minus natural log of cosine x plus c. You can leave it like that. Now your book, I think, changes it to secant, right? You don't have to. This is perfectly fine. But if you find it on a table of integrals and it's secant, what they did is they did a little bit of more processing, right? They put this minus to the top, so it was cosine x to the -1, so 1 over cosine is secant. I don't care. This is good.